Wait, no.
If lambda is an eigenvalue and your operator is a, then the operator a minus lambda has a kernel.
Yeah.
So it can't possibly be invertible.
Okay.
So the generalization is the spectrum of a function of an operator is all those complex numbers lambda such that a minus lambda is not invertible.
So it's just all eigenvalues?
In finite dimensions, it's just eigenvalues.
Okay.
In infinite dimensions, it's, well, there's a lot more than just eigenvalues.
What's an example?
So one example is, suppose you have a number, and suppose you can find vectors such that x minus lambda of, let's say that you find a sequence of vectors v sub I, such that x minus lambda of v sub I goes to 0.
Okay.
It's never actually 0, but it keeps getting closer and closer to 0. Well, then x minus lambda can never be invertible, because the inverse of x minus lambda would have to send these really, really tiny things to really, really big things.
Okay.
Right? So that's the approximate point spectrum. But there's a bunch of other stuff.
Okay, so he was playing around with the Laplacian.
No. So it's an old problem. An old problem is, so given a region, you can figure out the eigenvalues of the Laplace operator, like with some nice conditions on it. You know, like the boundaries, not that. So one question that people ask is, can you hear the sound of a drum?
Okay.
Can you hear the shape of a drum? So meaning the Laplace operator, the spectrum of the Laplace operator depends on the shape of the region.
Okay.
Right? Different shaped regions give different spectrums for the Laplace operator. Well, then someone asks, if you know the spectrum of the Laplace operator, can you figure out what shape its base space was on?
Okay.
So the answer is no. But the theory developed where this is all asymptotic. So these eigenvalues, they go to infinity, and there's the functions for the eigenvalues have like error terms, like big O of x squared or something. Like they have error terms that bound how fast they get big or whatever. So, but I mean small things, not x squared. So one of these error terms for the Laplace operator had the zeta function in it.